Okay, hello. We're looking at section 4.1 on random sampling. And one thing I've gotten feedback from some of the class is that, at least for the discussion questions in the text, it might work well for a face-to-face class, but with online, I'm kind of reading it through, you don't really have any interaction. So I'm going to be your interaction, so you don't just sit there reading to yourself. So what you can do on these is when you get to a slide with these, you can pause it, read it, familiarize yourself with it, and then replay because I don't want to read word for word all of these slides. So in this first discussion, we're looking at the difference between a census and a sample. And a census is when we're going to take everyone in the entire population. Like in the United States, every 10 years we get data on the entire population of the United States, or at least most of it. And a sample is when it's just not practical, either in terms of time, money, energy, to get that entire population. So we just take a limited group, get the results for that group, and then extend it out to the population. In terms of the answer for these, let me just discuss that first one a little bit. An automobile manufacturer inspects its new models. I don't know that there's a clear answer to this. It really depends on how in-depth the inspection is. So if it's a really brief kind of overview, let's check the brakes, let's check the gas, then probably each one is inspected. You would hope that there's some kind of inspection process that, yes, this car has been certified for use. On the other hand, if it's a very in-depth inspection of some of the smaller parts, that one is probably only done sporadically, every 1,000th model or something like that. So yeah, it wouldn't be realistic to do it for every car. On the other hand, a car is something that's very important because of the safety of its passengers. So more than perhaps other things like the candy or the cookie manufacturer, where it really doesn't matter how many chips are per cookie, there would be more of an inspection for each car. So more tendency towards the census in that first one. This random rectangles activity, and I'll let you read the instructions, but basically you're supposed to look at this page and choose 5 of these rectangles at random. So bam, 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 however you want to determine random. And what this activity gets at is our concept of random is not really random. So probably what would happen if I'm just going bam, 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 I'm probably going to tend to get some of the bigger ones. Whereas if I just put 100 numbers into a random number generator and looked, I would tend to get more of these small ones that I'm not going to hit as likely. Or maybe you're a person who, for some reason, tends towards the small. You think really cute miniature things are awesome. My daughter loves little Japanese toys that are miniature and cute, so maybe she would go directly towards these smaller ones, which would still be non-random, just in a different direction. So this goes through an activity. This is a plot of what you might get. So judgment, or human perception, what they think of as random. And notice again you have some small ones out here, but also some very large ones. The actual mean, I believe, is around 7, a little over 7. So you can see in general the human judgment was a little bit high on what they felt was a random sample of the rectangles, and these were the actual when it was actually done random. Another thing to point out is even when a sample is taken randomly, it doesn't mean it's exactly representative. So even in this random sample, we had, if it's 7.5 or something like that, the actual mean, we had one sample that was up here at 11, had a mean of 11, one had a mean of 3. So certainly even randomness can be off, but for reasons we'll look at later, there are a lot of advantages to randomness. Okay. one thing I want to point out here, if you take a simple random sample of 6 students or of 6 anything, you're probably not going to get that representative as a sample. Why? Because it takes larger samples in order to start really representing the population. For example, if you have a class of 40 students, maybe 20 male, 20 female, and you just choose 2 students at random, the chance that you will get 1 male and 1 female is about 50%, or exactly 50%, which means half of the time you'll get either 2 males or 2 females, which is totally not what you would use as a representative sample in terms of gender. So that's why we tend to look for larger samples. To give it a specific number is hard. Often 25 or 30 for finding a sample mean is given. But we'll look at some of those guidelines a bit later on as we get into inferential testing. One thing I just want to point out here, we're looking at water quality, and it says, is a census a possibility? So first of all, we tend to think of populations as people, and in this case, a sample is just a test tube of water, or in this case, I guess, 20 test tubes of water. So what is the population? Well, the population here would be the entire lake. So certainly we would not be able to test the water quality of every ounce of water on the lake, which is why we would do a sample. And in most cases, a census is rarely feasible when we're looking at any kind of large body in nature or humanity, sociology. Samples are much more practical. Okay, here's a puzzle. You may pause this, read it, and try to take a gander yourself. Simple random sample of 10,000 characters. So we could list all the characters of the book and randomly use a random number generator to get 10,000. That would be extremely time consuming. Another method might be if it's a 300-page book, maybe first we choose 10 pages at random, and then on each of those pages we take the first 1,000 characters. An advantage of a method like this, it's very feasible, something you could do pretty quickly with Word and some cut and paste, maybe Excel. Disadvantages, we wouldn't get a truly random sample. So again, I had mentioned 25 or 30 is a nice number to get a good estimate of the population mean. If we're just choosing 10 pages of the book, is that really going to represent? Well, it's very possible that there's certain parts of the book that are different than other parts, and we may or may not get those. For example, there may be a book with a lot of pictures, and if we get some of those picture pages, we might not have many characters at all, or they may be a very different type or pattern of the characters. And I know this is hard to read. I'm going to make it a little larger there. So a stratified random sample is a really important idea. There's times when we don't trust randomness fully. So we know that randomness is powerful, but somehow we want to override it. I'll give you an example. In my dissertation, I worked with looking at different groups of students and how they did in mathematics in high school and in college. And the sample I worked with wanted to make sure that there were enough Native American students or different minority populations that could easily get overlooked in a random sample. So instead, we made sure that first we stratified it into the different groups, ethnicities or locales, and then once we did that, looking at making sure we get a certain percentage of the population from each of those each of those groups. So it guarantees us, we can control, hey, I know I will get 100 Native American students in this sample because I'm going to take the entire Native American student population and randomly choose 100 from there. So you're taking away some of the control from the randomness into your own power, which is potentially good, potentially dangerous. So here we have some kind of cement plant, and we're looking at, I forget what some measure of air quality here. And you can see that near the cement plant, we have very high levels, and as you get further away, that entire last row are some of our lowest numbers. So you can see that pattern that's developing. So let's think a couple different ways we could sample this. We have 100 units in our population, so we could choose 10 of them at random. So maybe we end up with 2 from the first column, maybe we have 3 from the second row. We're just using a number generator to get 10 overall. And that's a simple random sample. Or we could do a stratified random sample where we say, okay, first we're going to divide it into these columns. Once we do that, we're just going to choose 1 from every column. So notice we could not get this 97 and this 92 like we could in a simple random sample. We're forcing ourselves to just get 1 in each of these columns. Similarly, we could go by the rows, just get 1 per row. And in this case, that makes a lot more sense because the row is more or less the distance away from that cement plant, which is the driving factor, looks like, in how much of that air quality is affected. So because we're able to, when we stratify by row here, we're able to reduce our variability. And let me show you what I mean here. So what are we looking at here? These are those 3 different ways to take the sample, a simple random. If we divide it into column and take 1 per column, or 1 per row. So how do they look so drastically different, and what does that even mean? Well, one thing I should point out is when we're looking at inferential statistics, variability tends to be our enemy. We want predictability as much as possible. We want to get as close as possible so that our estimate is very accurate. And if we start to get a range like this, we don't really know where the true, I mean, here's our best guess, but it could be out here, it could be out here. We have this wide range of potential values for the actual population value we're looking for. Notice the random sample is a little better than that column, but the row strata was incredibly tight, packed together, low variability, which is awesome because we can be pretty confident that the mean is somewhere right in here instead of leaving this wide room for interpretation over these. So why did that happen? Columns as strata was just kind of a arbitrary choice, and it turns out when you do stratified random sampling, you usually want some kind of purpose or guiding reason. Otherwise, you're probably better off just taking it randomly. But if you do have good justification, like in this chart, we could see that the further away we are, the lower we should get of that pollutant, the further we are from the cement plant. So it makes sense to take 1 per street. And so in that case, it did help us out by reducing that variability. So again, variability tends to be a bad thing here. Okay, and let's make this our last one for the video. We have an administrator wants to figure out how long they're taking. So he's going to stratify them according to class year. So this is good because we'll get, we're guaranteed to get some freshmen, some sophomore, some junior and senior. Why that's good is because usually freshmen and sophomore are required to live on campus, whereas older ones are not. What is potentially bad about this plan? Potentially bad. even among the juniors and seniors, you're going to have some on campus, so it may be better to divide on campus and off campus would be a better way of reducing that variability.